Hey, all right. So I'm gonna just put up a little warm-up exercise, and hopefully a few more people show up. But if only like one or two people come, I'll probably just convert this into like an office hours or something. But anyway, for now, here's the warm-up. Um, so let's say f of x is 1 minus x squared over x with, you know, natural domain. Right. Then uh, give with proof the values of the limit as x approaches infinity of f of x, the limit as x approaches 0 from above of f of x, the limit as x approaches 0 from below of f of x, and the limit. And this is, of course, when they exist. The limit as x approaches negative infinity of f of x. So yeah, I'll just say we'll resume, let's say 5:15, just to give people time to show up if they're going to. And yeah, like I said, if no one else shows up, this will just probably become like a second office hours. Okay, so also I have to apologize in advance if you guys talk, which is fine, obviously, but you might hear yourself echoing because my headphones broke recently, so I don't have any headphones anymore, at least not for another week or so. So sorry if that happens, but of course you're still like, please feel free to ask questions and stuff like that. So so to do these problems, I think it's just easiest to try to formulate the like you know, sort of the epsilon delta style like properties that we're trying to prove. Okay, so because we don't really, the problem is like what you'd like to say, right, is that this is like 1 over x minus x, right, for x not equal to 0, which is the domain. I mean, the domain is, right, the natural domain of this is like r without 0, right? So so what you'd like to be able to say is like, okay, you know, the limit as x approaches infinity of this function is negative infinity because negative x approaches negative infinity and 1 over x approaches 0. So like the sum should approach 0 minus infinity, which is negative infinity, right? But I think like technically speaking, we don't quite have general theorems to prove that, although there are like exercises that ask you to prove that, you know, when one like when one of the two functions that you're adding together is like, you know, bounded or has a limit or something, and then the other one approaches infinity, then the sum of those two functions will approach whatever like infinity the one of those two approaches. We don't have theorems quite like that, so technically we kind of have to go through these little like, not epsilon delta, but you know, it's like capital M and like delta or like alpha or something. So let me just show you what that would look like for, let's just, honestly, actually, I'm gonna just handle two of these two because I think these two are just like literally mirror images. In fact, you might even literally be able to argue that they're mirror images in the sense that like f of negative x equals negative f of x. So whatever these two limits do, these two have to do like the opposite of that. So whatever limit this is, this has to be the negative of that, and this limit has to be the negative of this one. So you can actually use that to kind of like cut it in half. So let's just do the first two. So let's look at like limit as x approaches infinity. So we claim the limit as x approaches infinity of f of x equals negative infinity, right? So what do we want to show? So let's phrase the property like the property that you would make, that you would phrase for like discussion 20.9, you know, where it's like, you know, every type of limit has its own like, for each blank there exists blank such that blank implies blank. Let's come up with that property. So in this case it would be for all m there exists an alpha such that for all x greater than alpha, we have f of x is less than m. This is actually the property that we would want to prove for this. Does that make sense? Okay, so so if this is what we want to prove, then so we can let m be a real number, right? And then so how do we choose alpha? Well, note for alpha, let's say alpha greater than or equal to 1, we have 1 over x is less than or equal to 1, right? So, well, what we can say is f of x. So in particular, 1 over x is less than or equal to 1, I guess, actually is more important. Yeah. we don't need the absolute values. So let's just say 1 over x is less than or equal to 1. So f of x is less than or equal to 1 minus x, which is less than or equal to 1 minus alpha if x is greater than or equal to alpha. Or actually, let's make these strict, right? So we want 1 minus alpha less than m, meaning alpha should be greater than 1 minus m, right? So pick alpha. Oh, I guess we can make this one less than or equal to, it doesn't matter. So pick alpha less than 1 minus m, then for all x greater than alpha, the above logic shows f of x is less than m, right? So that's enough to show that, you know, at least if you take for granted that, you know, that this property here is equivalent to the limit being negative infinity, which it sort of trivially is just by the, you know, by theorem, it's really, it all comes from like theorem 20.6, basically. Oh, I guess, or yeah, okay. There's analogs of theorem 20.6. I don't know. I think you can. I think it's perfectly fine to just take for granted that this is a valid way to, you know, describe this. If you really wanted to, you could just work with sequences instead, you know, and say that like all sequences approaching you know, where xn approaches infinity, have f of xn approaching negative infinity. That's also fine. And you wouldn't have to even change the proof that much, honestly. Okay, so then for the second one, we were trying to show that the limit as x approaches 0 from above of f of x, we're going to claim is, it should be infinity, I think, because it's 1 over x minus x. So yeah. So for this, the property would be, you know, for all m, there exists a delta greater than 0, such that for 0 less than x less than delta, we have f of x is greater than m, right? So note that for x less than delta, we have f of x is, you know, greater than 1 over x minus delta, right? So, yeah. Yeah. So, and then also, actually, it's greater than 1 over delta minus delta, I guess, right? Because, yeah. So if, oh, and if delta, okay, this is like, okay, you can make it easier by saying if delta is, right, sorry, this is what I really meant to say. If delta is less than 1, then f of x is greater than 1 over delta minus 1. So pick delta less than the minimum of 1, and then here it's like we would want, so if we want 1 over delta minus 1 to be greater than m, then add 1 and then invert it. So we want delta less than 1 over m plus 1, right? And I guess, honestly, we can also assume without loss of generality that m is greater than 0. Because if you can do this for m greater than 0, then of course you can do it for all like negative values of m, or m equals 0, just by like just replace m with 1 and then pick delta that way, right? So that way we ensure that this is never like randomly, infinity or something. And so I think this should work. And also, actually, I realized that in this one, we want to pick alpha should be less than like the minimum of, why did I say alpha less than? It should be greater than. Alpha should be greater than the maximum, sorry. The maximum of 1 and like 1 minus m. Yeah. Okay. Anyway, yeah, sorry for the confusion there. So does this, do you have any questions about this? Either of these? Okay, yeah, I think the takeaway here, I think, is like familiarizing yourself with these kinds of statements, and like being able, like, you don't have to memorize all of them, right? But it's more like if you understand the principle behind how these statements come about and how they reflect like the structure of the original limit, so like the fact that we have this here and this here, how these things are related, is very valuable, I guess. Yeah. Okay, so since there's only like 2 people, I'm thinking I'm just gonna basically treat this like office hours now. So if you guys have any questions, feel free to ask them now. I guess I can still put up some exercises if you want. There's like one or two more exercises I could give. It's up to you guys.
Can I ask a question regarding the previous one?
Sure, yeah.
Just a general question, like, how do you decide like whether you choose delta to be the minimum or the maximum?
Mm-hmm. Well, in this case, it's because we know that there are these like desirable conditions that are true whenever delta is like less than a certain thing, right? And whenever
Yes.
x is less than delta, so it's like we needed delta to be less than 1 for this to be true, right? And then of course we also need delta to be, well, delta can be less than or equal to this. It doesn't really matter, but as long as delta is less than or equal to this, then whenever x is less than delta, and if delta is less than 1, then this will be true, which is, or rather, then f of x will be bigger than m, which is what we want, right? So the fact that the requirements here are like going in this direction where delta has to be less than this and delta has to be less than or equal to this, then we want the minimum, because otherwise, if we took the maximum, it would be possible that delta could be bigger than one of them, and we need delta to be less than both.
Yeah. So when we require it to be less than both of them, we can use the minimum, right?
Yeah, exactly. Yeah. And if you need something to be bigger than 2 things at the same time, that's when you use the maximum.
All right, that makes sense. Thanks.
Mm-hmm. Any other questions? Let's see. And so, by the way, so because because I'm kind of converting this into office hours, I think I'm not gonna post this, so you don't have to worry about like if you want to ask questions that you wouldn't normally ask, if it were gonna get posted, uh, feel free. Let's see. Hmm. Okay, actually, yeah. So let's do sort of a generalization of like the stuff I was just talking about. So, for example, so this is like exercise 20.20. Oops. So, let f1 and f2 be functions such that the limit as x approaches a along s of f1 of x is plus infinity, and the limit L2 limit as x approaches a along s of f2 of x exists. So part A asks, show if L2 is not negative infinity, then the limit as x approaches a along s of f1 plus f2 of x equals infinity. So that's part A, and then there's a bunch more stuff. Let's just focus on part A. I don't want to get bogged down in the other parts with that. The other parts are about multiplication. So yeah, let's just focus on part A. So actually, yeah, I guess I'll go ahead and give you guys some time to work on it. And in fact, yeah, I guess I can also make I'll go ahead and make a room for you if you want to talk to each other about it. Of course, you don't have to, but yeah. So here's let's see. Yeah, so let's take like maybe 10 minutes. And yeah, there you go. So we'll resume at like 5:43. Okay. Hey guys. So let's see. So we want to show that this limit is infinity, right? So ultimately what that means is we have to let xn be a sequence in S with xn having limit a, right? And again, remember that in all of these like cases where you're looking at a limit where x approaches a along some set S, a can actually be plus or minus infinity as well. But not for like one-sided limits, like limit as x approaches a plus, or like limit as x approaches a minus. Those are not, these can never be, a is never infinity in these contexts, but for a like for an arbitrary set S, it can be infinity. Okay, so anyway, let's see. Right, so xn, the limit of xn is a, and right, then, and so we want to show that f1 plus f2 of xn goes to infinity, right? So let's let m be a real number. And we want to find capital N, right? So what we have to realize is that actually, so well, first of all, what do we know, right? We know that from our assumptions that f1 of xn goes to plus infinity. So we know f1 of xn goes to infinity, and f2 of xn goes to L2, which is not negative infinity, right? So there's actually a very elegant, or well, yeah, I mean, I think the most, like the sort of most efficient way of making the argument that f1 plus f2 of xn goes to infinity involves first bounding f2 below. Okay, so you can, so what we can say is so f2 of xn is bounded below, i.e., so there exists some, you know, let's call it, I don't know, m prime, such that f2 of xn is greater than or equal to m prime for all n. Okay? So the reason for this is that otherwise, right, for each, let's say for each k, we could select nk so that f2 of x and k would be less than negative k, right? So then x and k would approach a in S, but f2 of x and k would approach negative infinity, which is not allowed, right? So right. So do you guys understand this argument? We've seen this kind of thing before, you know, a number of times by now. But yeah, in this case, because it's a combination of two things, right? It's the fact that f2 of xn as a sequence, f2 of xn actually has a limit. Like it doesn't just like diverge completely. It actually has some limit, right? The fact that the limit exists here and the fact that it's not infinity combined mean that f2 of xn is bounded below. Okay, so that's kind of right, because we know the reason that f2, or sorry, the reason that right, the reason that this is actually a contradiction is because if this is a subsequence of f2 of xn, and if this subsequence approaches negative infinity, but the original sequence actually has a limit, then that means that the original limit would have to be negative infinity, right? So if you don't assume that the original sequence has a limit, then you can't like make that deduction. But yeah, anyway, so this is not allowed. So f2 of xn is bounded below by some number m prime is what we're calling it. So then you can say, so we know, f1 of xn plus f2 of xn is greater than or equal to f1 of xn plus m prime for all n. So, and we want, right? We want to pick capital N such that f1 of xn plus f2 of xn is greater than the given m, right? So it suffices to ensure that f1 of xn plus m prime is greater than m. So pick capital N such that for n greater than capital N, we have f1 of xn is greater than m minus m prime. This is possible because we assumed f1 of xn goes to infinity, right? Well, really, we assumed that the limit of f1 as x approaches infinity is infinity, but that means that any sequence like this, f1 of xn, has to approach infinity as well, right? So we can find this capital N, and this is enough, right? So then for n greater than this capital N, we have f1 plus f2 of xn is greater than m as desired. So so the limit of f1 plus f2 of xn is infinity, and since xn was arbitrary, we conclude that the limit as x approaches a along s of f1 plus f2 itself as a function of a continuous variable is also infinity, which is what we were trying to show, right? So so that's that, and that is like, it is like a generalized version of what we were talking about before, right? And if you look at what we were doing before, ultimately all of this stuff basically boiled down to like bounding one of the two terms above or below by some like constant number, basically, right? So I was here when we were looking at as x approaches 0, remember the expression for f here is like f of x is like x minus 1 over x. I was just looking at this and I was saying like, okay, this term becomes irrelevant, right? I mean, this term becomes irrelevant as x or sorry, the other term. Oh, it's the other way around. 1 over x minus x, right? This term becomes irrelevant as x approaches 0. So we should just be able to bound it by some constant, when x is close to 0. And then this is the one that we can force to get really big. So we can just basically, by bounding this term, we can make sure that it doesn't interfere too much with the one that's important, right? And then in the other one, it was like, this is the term that was irrelevant, and we bounded it above by bounding x below by some constant, and then this is the term that we were able to force to get very large, basically. Okay. But so we just went ahead and kind of made that argument in general for like two abstract functions. All right. Yes, I don't think there's really enough time left to do much more unless you guys have any questions. So I think I'm going to call it for now. And I think I actually will post this in the end because it sort of ended up working out, you know, functionally like more or less the same way as a normal discussion. So yeah, I think I'll go ahead and post it. But unless you guys have any other questions, I think that'll be it for today.
Thank you.
Mm-hmm.
Bye.
Yep. Bye-bye.